So we're going to continue talking about second order linear homogeneous differential equations with constant coefficients. Remember there were two types that we didn't know how to solve yet. Sorry, this is a y double prime. You can't really see that. Hopefully now you can. Here's the differential equation, and remember we can go right to writing the characteristic equation, replacing the double primes with r squared, single prime with r. Just a y is going to be the constant term. And then what's going on with this differential equation? Why don't we like it? Well, we have can't factor, so we're going to use the quadratic formula. 16 minus 4 times 1 times 13 is 52 over 2. So let's see what we get. This is negative 4 over 2 is negative 2, plus or minus, this is the root of negative 36. So that's 6i divided by 2 is 3i. Okay, so what don't we like is that these are complex roots. And actually, you can do the exact same thing we do with real roots. So you just take some arbitrary constant a, e to the one of the roots times t. It's just going to look a little bit uglier, but this is a perfectly valid solution to this differential equation. Plus b, e to the negative 2 minus 3it. And e to some power is a perfectly nice function to differentiate in complex numbers. You follow the same rules, so you're going to do a little bit of chain rule when you differentiate it. And if you were to plug this solution in to this equation, it would totally work. So this is valid. But the problem is how to interpret it. So usually this differential equation comes from something that requires real numbers, such as motion. If you had y double prime as the acceleration, y prime was the velocity, and y was displacement, then you probably don't want a complex solution, because what does that mean if we're just moving in one direction? We need some complex number knowledge in order to interpret this complex solution. This is all stuff that you may have seen in pre-calculus, but you may not have. All pre-calculus curriculums are taught differently. So we'll just go over it, and some of this may be review for you, and some of it may not. So we know this. I is some creature that you square to get negative 1. This is the better definition of I. The bad definition of I is I equals the root of negative 1. The root of negative 1 is actually okay. Radical negative 1, which is what this symbol means, is not good. This is not as good. Why? Let's just see why. Well, if I is the root of negative 1, then I squared is root negative 1 times root negative 1, which is the root of negative 1 times negative 1, which is negative 1 squared. I'm just following exponent and radical rules. And this is going to be the root of 1, which is 1, which is not what we wanted. We wanted I squared equals negative 1. So this is the superior definition, in case you were wondering. So don't touch I unless you have an I squared. That means every number, if we introduce I into our world, which has all real numbers already, is some real number A plus some real number B times I. And we can't get rid of this I. You can get rid of anytime you have an I squared, you get negative 1. Anytime you have an I cubed, you get negative I. Anytime you have an I to the 4th, we're just continuing to multiply by I, right? So we get negative I times I is negative 1 times negative 1 is positive 1, and so on. So all higher powers of I you can get rid of, but this one of the i's stays. So now you have two real numbers, A and B. Well, in math, if you have two real numbers, then we think of graphing it on a Cartesian plane. We actually call this now the complex plane, but with Cartesian coordinates. Okay, so we can graph this. We have a real axis, RE for real, IM for imaginary axis, and then you just have some point A plus BI, where here's the real number A, here's the real number B. Go over A and up. Easy. Okay. But what sometimes is more meaningful is if we switch from Cartesian coordinates to polar coordinates. Here's the part of pre-calculus that maybe sometimes doesn't get taught. Okay, so we're going from a comma b now to r comma theta. And then hopefully this is sort of review for you, but maybe not. So we're in polar graph paper. So regular graph paper is what I have here. You've got vertical lines actually tell you where you are on the x-axis. Horizontal lines tell you where you are on the y-axis. Sounds a little backwards. Now we're going to have circles telling you how far you are away from the origin. That's polar graph paper. I can't draw very well. Circles telling you how far you are away from the origin. And then angles. So these are rays. So starting from the origin going out, that tells you the angle we make with the positive x-axis. So if I'm over here, then the angle is an obtuse angle. We go all the way around. If I'm down here, then the angle is going to be over 180. And then we can go all the way up to 360 degrees. Or usually we're in radians, actually, so 2 pi. So this one is, so here's theta equals pi over 2. Theta equals pi. And we can go, for example, this is also theta equals 3 pi. We just go all the way around and then a little bit more. Okay, so lots of possible values for theta. Sometimes a couple different possible values for r. We can talk about r being positive or negative. Hopefully you remember all of this sort of. Okay, so r is going to be your distance to 0. And we actually have something in real numbers that's a distance to 0. We've actually talked about this. The definition for absolute value in real numbers is distance to 0. So we're just going to keep that. We're going to say the definition for absolute value in complex numbers, for some complex number z, is distance to 0. And then in complex numbers, there's a couple other fancy words. Sometimes we call this a norm. Sometimes we call it a modulus. All of those, norm, modulus, absolute value, they all mean distance to 0. Okay, and then we've got some triangle stuff going on, right? We got a right angle triangle here. We've got the legs are length A and length B, and the hypotenuse is length R, or absolute value of z. So we can actually calculate that. That's going to be a squared plus b squared. Okay, and now that we're in complex numbers, we can actually factor this by difference of squares. This we're going to write as a squared minus bi squared. Check that out. That makes sense, because this is b squared times I squared. I squared is -1. With this -1 is a plus. Okay, make sure you believe that. And then we can factor by difference of squares. So this is a minus bi times a plus bi. And then we note that start a new page so that we're not scrunched up in the bottom. That is actually, here's our complex number z. That was a plus bi. This is a minus bi. We call this the complex conjugate of z. Okay, you don't necessarily need to know that right this minute, but complex conjugates are really important for something like if you end up with something in the denominator, like complex number in the denominator. We don't like leaving complex numbers like this. We like having complex numbers as real number plus other real number times I. So if we have this, the solution to make this better is to multiply top and bottom by the complex conjugate. And as we saw from before, the product of those two is going to be a squared plus b squared. So I can actually rewrite, oh sorry, this is a minus, just from right there. So I can actually rewrite my 1 over a plus bi as, this is a little bit ugly if you separate it out, but here's a real number, a over a squared plus b squared, and another real number, negative b over a squared plus b squared I. Is this better? This doesn't necessarily look better. It looks a little bit uglier than what we started with, but it's in our complex number format, and if we wanted to graph it on the complex plane, we would know what the x and y coordinates are. So that's what's better about that. All right, one more thing. We're going to do some more right angle triangle stuff. So if this angle is theta there, then from trigonometry, right, that length is r, then we know that b is r sine theta and a is r cosine theta. That's from just this right angle triangle. Okay, so then we get z equals a plus bi is going to be r cosine theta plus I r sine theta. And that's probably our most important equation in this lecture.